Hi folks! The following video is our first one on alcohols. I'll talk about alcohol structure, acidity, and methods for preparing alcohols. Alcohol molecules contain an OH group, sometimes known as a hydroxyl group, attached to a carbon. In the same way we classify alkyl halides, alcohols are also classified by the number of carbons attached to the alpha carbon. The alpha carbon is the one attached to the OH group, and if this position has one other carbon group attached to it, it's considered primary. If it has two other carbon groups attached to it, it is secondary, and if it has three other carbon groups attached, it is classified as tertiary. An important physical property of alcohols is that they tend to have high boiling points. This is because the OH group can participate in hydrogen bonding. Let's consider the simplest alcohol, methanol. An electron-rich oxygen group can donate a pair of electrons to form a hydrogen bond with the hydrogen of a neighboring alcohol group. This is an attraction between the partial negatively charged oxygen and the hydrogen of a neighboring molecule. The acidity of an alcohol is another important property of it. Alcohols can be deprotonated by many bases to form the conjugate base of an alcohol, known as an alkoxide. Alcohols typically have pKa's ranging from about 15 to 18. There are a couple of important sets of reagents that are used to commonly deprotonate alcohols. One of these is strong bases, but especially sodium hydride. The hydrides lone pair can serve as a base to deprotonate the alcohol. This reaction forms the alkoxide conjugate base, and it also forms hydrogen, H2, which is a gas. This reaction is extremely favorable because the hydrogen gas simply bubbles out of solution, meaning that the reaction can't go in reverse. Another popular choice for deprotonating alcohols is treating them with lithium metal, sodium metal, or potassium metal. I won't discuss the mechanism for this reaction, but it ultimately results in formation of an alkoxide anion. You can ignore the sodium cation, and this reaction liberates a half an equivalent of hydrogen gas as well. So here as well, forming a gas is very favorable. A couple of factors influence the acidity of alcohols. One of these is resonance. And recall that we're thinking about the stability of the conjugate base, the alkoxide form. We can see this resonance effect in action by comparing cyclohexanol to this aromatic substituted alcohol. Considering the conjugate base of each of these, the conjugate base of this molecule on the right places a new lone pair adjacent to a pi bond, so there is resonance in the conjugate base. This stabilizes the conjugate base, resulting in this molecule being a stronger acid. This is seen in its lower pKa value. Another factor that will influence alcohol acidity is inductive effects. These will also stabilize the conjugate base by withdrawing electron density due to nearby electronegative atoms. We can compare the acidities of ethanol compared to trichloroethanol, and we imagine the conjugate base of each of these molecules. The added negative charge on the oxygen of the trichloro molecule is stabilized by these electron-withdrawing chlorine groups in the molecule. This means that the conjugate base of this molecule is more stable, meaning that it came from a stronger acid with a lower pKa. I want to review some methods that we've already seen for preparing alcohols. One method is substitution reactions involving alkyl halides. If you have a primary alkyl halide, you can prepare an alcohol by treating the primary alkyl halide with a hydroxide anion. This reaction would occur by an SN2 mechanism, meaning you would have a nucleophilic attack and loss of the chloride leaving group in the same step. If instead a tertiary alkyl halide is present, you cannot perform SN2 reactions on a tertiary alkyl halide. So to get the substitution reaction to occur, you need SN1 as the mechanism instead, involving first loss of leaving group to generate a carbocation before nucleophilic attack. The best reagent here would be to use water as a weak nucleophile weak base, so that you would form the substitution product along with the E1 elimination product. Another series of reactions that we saw as ways to prepare alcohols were addition reactions to alkenes. We saw alkenes could be treated with acid under aqueous conditions, meaning water, to form Markovnikov alcohol products. Be aware that this method for making an alcohol generates a carbocation intermediate that can undergo rearrangement reactions. Another method for getting Markovnikov addition of an OH group without carbocation rearrangement, though, is known as oxymercuration demercuration. This is a two-step method involving treatment of the alkene with mercury acetate and water, where water is serving as the nucleophile, and in a second step, you're treating this with NaBH4 to remove the mercury. A third type of addition reaction to alkenes has anti-Markovnikov regioselectivity, and this is known as hydrogenation oxidation. The first step is treatment of the alkene with BH3THF, and the second step is treatment with H2O2 NaOH to convert a BH2 group into an OH group for your alcohol final product. For the remainder of the video, I'm going to be talking about new methods for preparing alcohols by reducing carbon-oxygen double bonds. Before delving into these methods, I want to talk about oxidation states first. We're going to use this as an electron bookkeeping mechanism to decide if a reaction counts as a reduction reaction, an oxidation reaction, or neither. To determine oxidation states, and we're going to be focusing on carbon oxidation states, we're going to treat all bonds in the molecule as purely ionic. You'll imagine breaking all of carbon's bonds to other elements, and when you break the bonds, you give the electrons to the more electronegative atom from that bond. To begin, I'll demonstrate for this molecule called formaldehyde. You're going to imagine breaking all of the bonds in this molecule and giving the electrons to the more electronegative atom from each bond. So we had a carbon-oxygen double bond with 4 electrons in it total, 2 in a sigma bond, 2 in a pi bond. Oxygen is more electronegative than carbon, so oxygen would get all 4 of those electrons from the bonds. Then we would look at the carbon-hydrogen bonds. Carbon is more electronegative than hydrogen, so from each carbon-hydrogen bond, carbon would get 2 electrons. And there are 2 carbon-hydrogen bonds in this molecule. We would look at how many electrons are assigned to carbon, and in this case it would be 4 electrons. You would take the number of valence electrons for the atom, for carbon this is always 4, and you would subtract the number of electrons around that atom in the molecule. In this case, also 4. The carbon oxidation state in this molecule would be 0. Now let's evaluate methanol containing a CH3 group attached to an OH group. Again, we'll focus on carbon, and we'll imagine cleaving each of its bonds and giving the electrons from the bond to the more electronegative atom. Oxygen is more electronegative than carbon, so oxygen gets both electrons from that bond. Carbon is more electronegative than hydrogen, so carbon gets the 2 electrons from that bond. And carbon had 3 different hydrogens attached to it. So 3 different pairs of electrons assigned to it. And in this case, carbon has 6 electrons around it in the molecule. We would take the number of valence electrons for carbon, 4, and subtract the number of electrons around carbon in this molecule, 6. And we would get the overall oxidation state for carbon in this alcohol as being -2. The reactions I'll be covering for the remainder of the video can be classified as reduction reactions. So first I want to define oxidation and reduction reactions. Oxidation reactions will result in an increased oxidation state, and for us in organic chemistry, we're going to be looking at the oxidation state of carbon specifically. Reduction reactions will be those that result in a decreased oxidation state, for us, for carbon specifically. A reduction reaction we'll be looking at today is starting out with an aldehyde or ketone with a carbon-oxygen double bond, and we're going to be adding hydrogens across this bond. To see why this counts as a reduction reaction, we could look at the oxidation states of these central carbons attached to oxygen in each of these molecules. When we look at breaking the bonds for the ketone on the left, for the carbon-oxygen double bond, oxygen will get all 4 of those electrons, and then for the carbon-carbon bonds, carbon has the same electronegativity as another carbon, so we distribute those electrons evenly. From the carbon-carbon bond on the left, the central carbon has 1 electron assigned to it, and for the carbon-carbon bond on the right, the central carbon gets 1 electron assigned to it again. Taking the number of valence electrons and subtracting the number of electrons in the molecule gives this central carbon a 2+ oxidation state. We can do the same thing for the alcohol on the right, again focusing on the central carbon. Oxygen is more electronegative, so it gets both of the electrons from that carbon-oxygen bond. Comparing carbon to hydrogen, that CH bond that's not drawn out, carbon is more electronegative, so it gets both of the electrons from that bond. And then for each carbon-carbon bond, the electrons are divided evenly. The central carbon has 4 electrons around it. Carbon has 4 valence electrons, so the central carbon has an oxidation state of 0. So in our reduction reaction, going from a ketone to an alcohol, the central carbon went from a +2 oxidation state to a 0 oxidation state. This counts as a decreased oxidation state, so we can call this a reduction reaction. The reduction reactions I'll be talking about today convert a carbon-oxygen double bond into an alcohol. And a term I might use to describe the carbon-oxygen double bond is that I can refer to that group as a carbonyl. I'll discuss 3 methods. The first of these is hydrogenation of ketones or aldehydes. A ketone specifically has a carbonyl attached to 2 other carbons, and ketones can be reduced to alcohols by adding hydrogen in the presence of a metal catalyst, either platinum, palladium, or nickel. This reaction adds 1 hydrogen to the carbon of the ketone and another hydrogen to the oxygen of the ketone, which converts this molecule into the alcohol. The same thing is possible with aldehydes, in which the carbonyl is attached to 1 carbon and a hydrogen on the other side. The hydrogen is optional to draw out. The same conditions, treatment with hydrogen gas and one of those same metal catalysts, will add a hydrogen to the carbon, a hydrogen to the oxygen, and convert the aldehyde functional group into an alcohol. You do not need to know the mechanisms for these reactions. but know the reagents and be able to predict the products. One consideration for whether or not you want to use hydrogenation is that you should be aware that hydrogenation also reduces alkenes and alkynes. So if you have an alkene in your molecule or an alkyne in your molecule and a carbon-oxygen double bond, you'll want to choose carefully whether or not you want to use these hydrogenation conditions or a different method that I'll discuss in a minute. A second method for reducing carbon-oxygen double bonds to form alcohols is using a reagent called NaBH4, sodium borohydride. This will react with either ketones or aldehydes to convert them into alcohols. In addition to NaBH4, you'll need a solvent with a proton that can be deprotonated on it, such as an alcohol or water. NaBH4 features a sodium cation and the borohydride anion, a boron with 4 hydrogens around it and a negative charge. You can use the sodium borohydride and the alcohol solvent in the same step, and these reduction reaction conditions will not react with alkenes or alkynes, so it has a different selectivity to hydrogenation. In the mechanism, it's important to think about what is our electrophilic site in the carbonyl. Due to the electronegativity difference, this carbon has a partial positive charge and oxygen has a partial negative charge. It is this carbon attached to oxygen that will behave as the electrophile. The first step of the mechanism is going to be a nucleophilic attack, and in BH4-, it is one of the boron-hydrogen bonds and the electrons in that bond that behaves as the nucleophile. The nucleophilic attack will have 2 curved arrows. I will draw this from the middle of a boron-hydrogen bond to the electrophilic carbon, and in the same step, I will break the carbon-oxygen pi bond and bring those electrons up to oxygen. This step forms a new carbon-hydrogen bond with a hydrogen from BH4-, and oxygen has a new lone pair and a negative charge. In the second step of the reaction, this oxygen with a negative charge is going to behave as a base, and the alcohol solvent will behave as the acid. This proton transfer step will generate a new oxygen-hydrogen bond in our molecule of interest, and it will deprotonate a solvent molecule. This step forms the oxygen-hydrogen bond of the final product. So in this reaction, I've generated a new carbon-hydrogen bond and a new oxygen-hydrogen bond. The hydrogen attached to carbon came from the BH4- nucleophile, and the hydrogen attached to oxygen came from the solvent, acting as an acid. For some ketones, the stereochemistry of this reaction will become important. Here's an example ketone where this will be the case. Notice on the 2 sides of the ketone I have 2 different groups attached to it. The ketone itself is not chiral though, because this carbon does not have 4 different substituents. I'm imagining treating this with the NaBH4 reduction conditions. In the product, I've added a new hydrogen to the carbon of the carbon-oxygen double bond, and a new hydrogen to the oxygen. Notice that the carbon has become a new chiral center. Because of this, I need to draw 2 stereoisomers of product. I could imagine the new hydrogen came in as a dash, pushing the OH group to be a wedge, or the new hydrogen could be a wedge, making the OH group a dash. The third type of reduction reaction I will discuss today uses lithium aluminum hydride, LiAlH4. This reagent will react with either ketones or aldehydes, and conversion of these into an alcohol involves 2 steps. First, treatment with LiAlH4, which features an aluminum with 4 hydrogens around it, with the aluminum having a negative charge. And then importantly, here in a second step, you need to add water or a different source of protons. This could be an alcohol, water, or H3O+. Most commonly, though, you'll see water. The reason we need to do this in 2 steps instead of 1 is that lithium aluminum hydride is much more reactive than sodium borohydride. Lithium aluminum hydride will react with the water itself instead of giving you the reaction you want with the carbonyl. So you need to add your reagents, lithium aluminum hydride and water, in separate steps, rather than having them present at the same time. The reaction mechanism, though, will look very similar to what we saw with NaBH4. The carbon of the carbon-oxygen double bond is the electrophile, and electrons from one of the aluminum hydrogen bonds can serve as a nucleophile. I will take these electrons to the carbon, which is forming a new carbon-hydrogen bond, and I will break a carbon-oxygen pi bond in the nucleophilic attack step. This first step breaks the aluminum-hydrogen bond. It transfers the hydrogen to the carbon. It breaks the carbon-oxygen pi bond and makes a new lone pair on oxygen, giving the oxygen a negative charge. The molecule will stay in this anionic form until the second step, when water is added. And then the anionic oxygen will act as a base in the proton transfer event. This will generate the neutral alcohol product. This reaction has added a new carbon-hydrogen bond and a new oxygen-hydrogen bond to the molecule. The hydrogen attached to carbon came from AlH4-, and the hydrogen attached to oxygen came from water in the second reaction step. Here as well, we have to pay attention to stereochemistry. If we have a reactant where your carbonyl has 2 different groups attached to it, this would add a new hydrogen to the carbon of the carbonyl and a new hydrogen to oxygen, generating an alcohol group. The carbon that's getting the new hydrogen attached to it is now a chiral center in the product, so you have to draw 2 stereoisomers. I would draw these with the OH group as a wedge or a dash. To end, I want to talk about preparing diols, molecules containing 2 OH groups. You can make these molecules using the methods we've seen previously, and you'll want to choose which reaction to use based on what position you want the OH groups to be in relation to each other. One choice is to prepare diols from diketones, molecules containing 2 ketones. This could also work for molecules containing 2 aldehydes. So let's imagine the following starting material containing 2 ketones, and that we want to convert it into the following product, containing 2 alcohols. Here I'm ignoring stereochemistry. One method that we saw for converting a ketone into an alcohol is to treat it with hydrogen and a platinum catalyst. Another method is you could use sodium borohydride and methanol, and that would react with each of the carbon-oxygen double bonds to convert each of those into an alcohol functional group. Or you could react the ketones in the molecule with lithium aluminum hydride, followed by water in a second step. Each of these reagents would react with both of the carbon-oxygen double bonds in the molecule, add a hydrogen to each of those carbons, and a hydrogen to each oxygen, resulting in a product with 2 alcohols present. Another method we saw for preparing diols, where the alcohols are on adjacent carbons, are in 2 reactions known as dihydroxylations of alkenes. A method we saw that results in anti-dihydroxylation is 2 steps. First treatment with a peroxy acid, RCO3H, and in a second step, treatment with an acid catalyst and water as a nucleophile. This reaction goes through a 3-membered ring epoxide intermediate, and in the second step, the epoxide gets protonated and the ring gets opened up, ultimately leading to the anti-addition of 2 OH groups. Another dihydroxylation of alkenes method that we saw results in syn dihydroxylation. We saw several sets of reagents for this, but one of those is osmium tetroxide with NMO, where in this particular reaction, the osmium tetroxide is acting as a catalyst. So notice the first case where I had preparation from a diketone, you could imagine those ketones could be anywhere in the molecule, and they could separately get converted into alcohols, whereas the alkene example will give you the alcohols on neighboring carbons in the product. Okay, so today's video talked about alcohol structure and acidity and ways of deprotonating an alcohol. I talked about reduction reactions and emphasized the carbon oxidation state as a method for determining if a reduction has taken place. I introduced 3 sets of reactions that will convert a carbon-oxygen double bond of a ketone or aldehyde into an alcohol. And I briefly talked about preparing diols, where you have a molecule with multiple OH groups present. That's it for this video. I will see you in class.